This video is looking at nucleophilic substitution reactions. So what is a nucleophile? Sometimes nucleophiles have a negative charge. One thing they must always have is a lone pair of electrons, at least one lone pair. Nucleophiles are attracted to areas of positive charge, as their name suggests. When they approach these areas of positive charge, which is normally going to be a positively polarised carbon atom, they donate the lone pair of electrons to form a new covalent bond with the carbon atom. So, some examples of nucleophiles. Many, as we say, have negative charges. So, hydroxide ion, the lone pair on the oxygen. A cyanide ion, slightly less common. This time the lone pair is actually on the carbon. And the chloride ion, which of course has 4 lone pairs. There are also uncharged nucleophiles. So we have water, which has a lone pair on the oxygen, and ammonia, which has a lone pair on the nitrogen. And these can behave as very good nucleophiles too. We're going to have a look at the reaction of nucleophiles with halogenoalkanes. Halogenoalkanes will react with nucleophiles because the carbon-halogen bond is polarised by the fact that the halogen atom is more electronegative than the carbon. So this makes the carbon have a slight positive charge, and the nucleophile, such as a hydroxide ion, can donate its lone pair to that carbon. Now, there are 2 ways that this reaction can take place, 2 different mechanisms for nucleophilic substitution. In this mechanism that's shown, everything happens in one single step. So as the nucleophile attacks that carbon atom, the carbon-halogen bond breaks at the same time. So the pair of electrons in the lone pair on the hydroxide ion attaches to the carbon. The carbon has 4 bonds around it, so in order for the OH- to attach to the carbon, that means that another bond must be lost. Both the electrons in the carbon-bromine bond go to the bromine atom to form a bromide ion. So our products, the hydroxide ion has essentially been substituted and a bromide ion is left in solution after the reaction's taken place. We have made an alcohol. There is another way that this mechanism can take place though, in 2 steps. So an alternative mechanism is that the carbon-halogen bond breaks first. This forms a carbocation intermediate, a little bit like the carbocation intermediates that have been seen before when we did the reactions of alkenes. And so the carbocation is therefore going to be ready to accept the pair of electrons from the nucleophile and form a new bond. Products are exactly the same. The kinetics and the rates of the reaction and the way these happen are slightly different. So the way you find out whether the first or second mechanism is taking place is to look at how the concentration of, for example, in this case, hydroxide ions affects the rate of reaction. So which mechanism is more likely? Can we tell just by looking at halogenoalkane which one is more likely to happen? The first mechanism where we have just everything happening in one step, or the second mechanism where the carbon-halogen bond breaks first? In the first mechanism, it's the nucleophile attacking that really encourages the carbon-halogen bond. This is more likely for primary halogenoalkanes, and there are 2 main reasons. There's more room for the nucleophile to attack on a primary halogenoalkane, because on a primary halogenoalkane you may have 1 carbon attached to the carbon with the halogen attached, but everything else will be hydrogen. So there's more room for the nucleophile to get in. There's no big carbon or methyl groups or anything attached. Primary carbocations that would form if you were to break the carbon-halogen bond without the nucleophile attacking, they're not very stable. They're very unlikely to form on their own. So if you leave a primary halogenoalkane, it's highly unlikely that the carbon-halogen bond will break of its own accord. Let's look at the second mechanism. In that mechanism, the carbon-halogen bond breaks first. So we form that positive carbocation intermediate, and then the nucleophile gets a chance to attack. It follows that this will be more likely in tertiary haloalkanes. For the same reasoning, you will have large, bulky carbon groups surrounding the halogenoalkane, not allowing space for the nucleophile to attack, and the carbocation will be more stable. It's also more likely that this second mechanism, where the carbon-halogen bond breaks, is more likely in iodoalkanes than chloroalkanes. And that's because the carbon-iodine bond is much, much weaker. So it takes a lot less energy to break. If you were to look at the rates of reaction for an iodoalkane and a bromoalkane and a chloroalkane, then that bond would break much quicker in an iodoalkane and the reaction would happen much, much quicker as well. So here's an overall balanced equation for the substitution of a hydroxide ion for the bromide in bromomethane. As you can see, it makes no difference what the halogen is. All you're doing is replacing one negative ion for another negative ion. So what happens if instead of a negatively charged nucleophile, which can directly substitute in for the halogen and produce a halide ion, you use a neutral, uncharged nucleophile? Well, let's have a look at the example with water. Bromomethane would readily undergo what we call hydrolysis, so that means breaking the carbon-bromine bond in water, using water as a reactant. And as you can see, the product, the methanol, is exactly the same as before. It's only the side product. Instead of making a Br- ion, we're making hydrogen bromide. The mechanism, again, will be very similar, and the first step will be exactly the same if we assume it goes by the first mechanism we looked at before. The carbon-halogen bond is polarised and the water has a lone pair. In fact, it has two, but we only need to draw one in the mechanism to show what's happening. That lone pair will be donated to the carbon in order to make a new bond with it, and the Br- will be lost as before. So the first step, as you can see, the curly arrows are exactly the same. The only difference is we started with two neutral substances, two substances with no overall charge. We lost a Br-, which means that bromine has gained the electron that it was originally sharing with the carbon. The oxygen has replaced that carbon's electron by donating its lone pair, but that means that it has now a positive charge. It loses that positive charge by losing H+, and that will form the normal situation where we see oxygen having just two bonds. So oxygen is in a sense there, getting its lone pair back from the pair of electrons that are shared with the hydrogen. The overall products then will be methanol, as we said, and since this is in water, we're unlikely to actually make undissociated HBr, although we might write that in a balanced equation. Actually, we're going to make hydrogen ions and bromide ions, which will be separate in solution. An overall equation for the reaction of ammonia shows us the same kind of thing happening. So here the ammonia would attack the carbon and the bromide ion would come off. This would leave the nitrogen with no lone pair because it's donated its lone pair and a positive charge. To get that lone pair back, it would lose H+. So the overall reaction, we are forming HBr as a side product. This is the structure of what would form, just so you can see, as it's quite an unfamiliar compound at AS level. The name of this compound would be ethylamine. So the amine is the NH2 group at the end, ethylamine simply because it has two carbons. Now you've had a look at nucleophilic substitution reactions, make sure, if you haven't already done so, that you're familiar with free radical substitution and electrophilic addition reactions.